So welcome to this next video, and it's on trig graphs. And one of the things we hope that you're going to pick up as you watch these videos is that in fact all these topics are interlinked, and the understanding in one helps you in the next one. So in the previous in the intro video, we reminded ourselves that all the trig ratios are positive in quadrant 1, sine in quadrant 2, tan in quadrant 3, and cos in quadrant 4. Now this helps us draw the graphs, all right? Here's a sine graph, and this is the basic kind of shape of the sine graph. It's a sort of gentle, smooth curve. It reaches a maximum value of 1, minimum value of 1. This is quadrant 1, okay, from 0 to 90 degrees. And we can see it's positive, it's above the axis. It's still positive in quadrant 2, and then it drops below the axis in quadrant 3 and quadrant 4. So the cast diagrams are a real guide to helping us learn to draw these things. We do need to learn these graphs. We need to recognize them like old friends. They have a couple of kind of characteristics. Unlike our paper 1 graphs, these graphs are what we call periodic. They actually repeat. So depending on what domain we choose, we might get, we will get a different picture. Right, this is from 0 to 360 degrees, so that's the domain. But we could take a different piece. We could take 0 to 720 degrees. So the first attribute that this graph has is what we call periodicity. So it actually repeats itself after a period of 360 degrees. That's a full kind of sine wave, and it looks like a wave. And in the next 360 degrees to 720, it will do another one. Likewise, it will do one between 0 and minus 360. It also has what we call an amplitude, and the amplitude is half of the vertical height. Right, the axis is what we call the mean position, the sort of halfway position, and the sort of distance from the mean position to the top is the amplitude. The range is exactly as we're familiar with our paper 1 graphs. The range is that y can take on any values between minus 1 and 1, including minus 1 and 1. Right, so we probably say from minus 1 to positive 1. Right, let's look at a cos graph. All right, remember cos is positive in quadrant 1, then it's negative in quadrant 2, it's negative in quadrant 3, and it's positive in quadrant 4. Right, if we look at, just going to zoom, scroll slightly back up. If we look at this cos graph and the sine graph, we'll see that they're incredibly similar, and there's a very good reason for this, which we'll get into shortly. The cos graph also has a period of 360 degrees and an amplitude of 1 and a range minus 1 to 1. You need to learn the pictures of these graphs. You need to recognize them. If you see a picture, you need to know which type of graph it is, and if you see an equation, you need to be able to draw the graph. The tan graph's a bit of a freaky thing because, well, let's go revert to the cast diagram. It's positive in the first quadrant, negative in the second quadrant, positive in the third quadrant, and negative in the fourth quadrant. Okay, it doesn't have an amplitude that's defined. It actually continues upwards forever. It's undefined in much the same way that a hyperbola is undefined. It's undefined at 90 degrees and at 270 degrees, and in fact every 180 degrees thereafter. All right, so these are vertical asymptotes. Next up, we're going to talk about the ways in which these graphs can be transformed. Right, in exactly the same way as we deal with graphs and functions in paper 1. If we add or subtract a number at the back, the function will shift vertically. Right, it will go up if we add a number, and it will go down if we subtract a number. If we add a number to the angle before finding the trig function, all right, before finding the trig ratio of that angle, then it gets shifted horizontally. And just like our paper 1 videos, paper 1 functions, sorry, if we add, it goes left, and if we subtract, it goes right. The next one, I'm going to jump to the last one, the change of amplitude. If we multiply a number in at the front here, what happens is that the graph gets kind of stretched if that number is bigger than 1, all right, or squashed if it's less than 1. It also, and we should probably just add this in here, it also gets reflected over the x-axis if a is negative. And then the last one, and this one's unlike anything we encounter in paper one, and that is a change of period. So if we were to multiply the angle by a number, what will happen is that the graph will get stretched if that number is less than 1, stretched out left to right, and squashed if it's bigger than 1. Right? And we'll then do A waves per 360 degrees, and its period will be 360 divided by A. That's for sine and cos. All right? Obviously, for a tan graph, its period will be 180 divided by A. We can investigate and explore the different graphs, the different trig graphs. So let's start off with a kind of vanilla sine graph. There it is. Positive in quadrants 1 and 2, negative in the next two, a range from -1 to 1, an amplitude, remember that's half the total height of the graph, of 1, and a period of 360 degrees. Cos graph, very similar, as we'll discuss. It's actually a sine graph that just starts 90 degrees kind of later. All right, and there we see it's got the same amplitude, same range, and same period as a cos graph. Tan graph's rather different. It has, as we know, it has asymptotes. They're not actually shown on here, but they're at 90 and at 270. Remember, tan is positive in quadrant 1 and quadrant 3. All right, negative in 2 and 4. Right, now I'm going to just manipulate the sine graph a little bit. So I'm going to start off with just kind of a basic sine graph and a vanilla sine graph. They're actually on top of one another. All right. The first one that we're going to look at is the vertical shift. If we add a number at the back after finding the sine of x, so for example, sine of x, close brackets, plus 1, what happens is that the graph will move up by 1. Sine x minus 1 will move down by 1. All right. So I've now moved it down by 2. What gets affected is the range. The amplitude is not affected, the height of the graph is not changing, and the period is not affected. Let's put that back. Next up, we're going to look at the horizontal shift, where we're going to add or subtract an angle to x before we find the trig ratio. Right, so for example, I'm going to work out the sine of x plus 20, x plus 30, x plus 45. And what you'll see is that the green graph is actually just the vanilla flavored purple graph shifting across to the left. And what we'll see, and it ties in exactly, all right, is that when we shift the sine graph 90 degrees to the left, we actually get a cos graph. And that shouldn't surprise us. It ties in exactly with our reduction stuff. Sine of 90 plus x. We're in quadrant 2, and we've come off a vertical axis. Sine's positive, so sine of 90 plus x is exactly the same as cos of x. Okay, that's our horizontal shift. Remember, if we want to move the graph to the right, then we must subtract from the x values. So, for example, if we sine of x minus 180, right, that's actually the same as sine of 180 minus x. If we add 360, which is just the negative of sine x. And you can see, in fact, what we've actually got a reflection in that case. Let's put that one back to 0. Right, the next one is that if we have a multiplier at the front, normally a sine graph maxes out at 1 at 90 degrees, and it's a minimum of minus 1 at 270 degrees. But if we were to multiply by 2, say at the front, what we see is we get a vertical stretch of the graph. The graph now gets up to a maximum value of 2. Remember, the green one is the translated one, the transformed one. The purple one is the original vanilla flavored graph. Right, so it actually kind of stretches it. It is affecting the amplitude and also the range of the function. Obviously, if I make it less than 1, like 0.4, again, it's now sort of been squashed. And then clearly, if I make it negative as well as 0.4, then it's kind of flicked over and maybe squashed, or flicked over and stretched. Okay, let's put that one back. The last one, and it's probably one of the most significant ones because it's kind of very different to anything that we encounter in our paper 1 graphs, is that if instead of finding the sine of x, we find the sine of 2x. Now let's just think about this briefly. Normally, sine maxes out at 90 degrees. In other words, it gets up to its maximum value at 90. But if we double the value inside here, then it will get there twice as quickly. All right. So in other words, if I draw sine 2x, sorry, let's just go back to sine 2x, we'll see that at sine 2x, the graph's already maxed at 45, because double 45 is 90, and sine of 90 is 0. Normally, by 90, on the vanilla one, at 180, it's got back down to 0. Now, because 90 is being doubled as the input, and it's going to get back down sort of twice as fast. What's been affected here is not the range, it's not the amplitude, but in fact it's the period. The period of this graph is actually halved. We've got twice as many graphs as usual. Okay, and this has quite big implications for solving of equations, but we'll come to that just now. Right, these sketches are all available on the CIMI website, so feel free to kind of engage with them and enhance your understanding of these things. Okay, let's put all that into practice and let's now find the equations of some graphs. So first up, to me, this looks like a sine graph that has been transformed. All right. The couple of things that I'm going to look at, it's starting at 0, 0. That suggests to me that it hasn't been shifted left or right vertically. However, it's going twice as high as it normally goes. So I'm looking at something like y equals 2 sine something. The last thing I'm going to check is the period. In fact, this graph is doing 1, 2, 3 waves per 360 degrees. It's y equals 2 sine 3 theta. Right, and because it's doing 3 and 360 degrees, its period, remember, is 360 divided by 3, which is in fact 120, and we can see that exactly here. After 120 degrees, it's done one cycle, one wave. Double that, 240, it's done a second one. Triple that, 360, it's done a third one. Okay, one of the things I didn't speak about when we looked at a tan graph, and I'm just going to zoom up to the kind of vanilla flavored tan graph. There it is. A really, really important point on a tan graph is that tan of 45 is equal to 1. That ties into lines with a gradient of 1 going uphill at an angle of 45 degrees, but that's an important point to kind of look out for. Okay, let's see if we can work out the equation of this graph. Well, first up, it seems to not be starting at 0. It looks like this graph has been picked up, okay, by 1. Looks like it's a tan graph of some description that has been picked up by 1. The asymptotes are where I would have expected them to be. That tells me that the period has not changed and that the graph has not been shifted left or right. So I'm looking at something like y equals 2 tan theta, and I'll explain why now, 2 tan theta plus 1. Right, and I'm being guided entirely by the position of this point over here, because tan theta plus 1 would go through 2 at 45. This is actually going through, it's being kind of stretched up and then lifted. Okay, this one, a cos graph which has a period of 720 degrees and a range of -2 to 2. Now remember, a cos graph normally has a period of 360 degrees and it would just be cos x. All right, this is in fact cos of a half x, all right, or half theta. We could write it like that, all right, or we could write it like this, cos half theta. Right, because I'm getting half as many waves as usual in an interval. All right. Now, normally a cos graph goes from -1 to 1. This one's going from -2 to 2, so the amplitude has been affected. This graph is 2 cos half theta, or as I say, we could write it like that. Okay, let's practice some more. Remember to keep pausing the video, trying them yourself. Right. This one, definitely a sine graph, starting at 0, 0. It hasn't been moved up or down, but the amplitude has definitely been affected. I'm going with 3 sine. Then I also see that I'm getting 2 graphs in, so 3 sine, 2 theta. Remember, if there's a 2 here, that means that the period would actually be 180 divided by 2. rubbish. The period would be 360 divided by 2. In other words, the period would be 180, and we can see clearly that the period is 180 degrees. That's how long it's taken. Okay, this next one is looking like a tan graph, definitely. There's an asymptote in here. Now that asymptote would normally be at 90, right? So I'm thinking something like y equals tan of a half x. Right, now tan of a half x, remember that point of 45 degrees and 1, right? Tan of a half x would actually, if we put 90 in for x, we would get half of 90, we get 45. So at 90, we would expect tan half x to be at 1. It's at minus 1. And so in fact, what we've got here is we've got a minus 1 in the front. It hasn't been shifted, but it has been reflected over the x-axis. Okay, this next one, the period seems unaffected. To me, it looks like a sine graph. We could probably manipulate it and give an equation for a cos graph, because remember, sine and cos are, you can move the one to become the other, all right? But I would go with a sine graph. The period hasn't been affected. The amplitude hasn't been affected, all right? The total height is 2, the amplitude is actually 1. Right, but it looks like this graph's just been dropped down by 1, so I'm going with sine theta minus 1. Right, what's been affected, obviously, is the range of the graph. This graph only takes on values between -2, or rather from -2 up to 0. Okay, so it's just a sine graph that's been dropped down 1. This next one looks very much to me like a cos graph, okay? Again, the period doesn't seem to have been affected. By the time we get to 360 degrees, we've done a full cycle, but it does seem that it hasn't started kind of, normally a cos graph would start at 0, 1, right? And it would hit the x-axis for the first time at 90 degrees. Now this one's hitting the x-axis at 70 degrees, okay? My answer for this one is that we are dealing with just a normal cos graph, that the amplitude and range haven't been affected, a normal cos graph that's been shifted left by 20 degrees. All right, and remember to shift a graph left by 20 degrees, theta plus 20 degrees. Okay, next up, there's 2 more here. All right, this one over here, again, I think we could get away with a cos graph or a sine graph here. If I'm going for a cos graph, I would be going with y equals cos. Now this is 45 degrees here, right? So it's maxing out at 45 degrees, right? It's been shifted 45 degrees to the right, so cos theta minus 45. However, it has also been shifted. If we picture this kind of continuing down here, this would be minus 45. We could just as easily go with y equals sine theta plus 45. Right, in other words, the sine graph shifted 45 degrees to the left. Right, G, the amplitude has not been affected in G. To me, it's looking like a sine graph that's been dropped down by 1. So something like y equals sine of some thetas minus 1. But if we look at the period, we're getting twice as many graphs in here as usual. The period is in fact 180, and the equation of this graph is y equals sine 2 theta minus 1. Right, now the last thing is to actually kind of draw some graphs, right? So we're now going to draw cos 2 theta and sine theta. Cos 2 theta, remember, is going to do twice as many cos graphs as usual. Now normally a cos graph would kind of go down to 90, to minus 180, to 270, to 360. That would be the vanilla flavored cos graph. This one is actually going to already get to 0 by 45. It's going to bottom out already for the first time at 90. It's going to hit 135 there, It's going to go up there, and then it's going to do exactly the same again. Okay, let's look at the other one. So that's f of x. The other one is sine theta, just a regular sine graph. Let's quickly draw that one. Right, remember, regular sine graph starts at 0. It's positive in the first quadrant, gets up to a maximum of 1 at 90 degrees, gets down to 0 at 180 degrees. It gets down to its minimum at 270 degrees, and then back up to 1. Okay, back up to 0. So this would be f. This would be g. Right. Now, one of the problems here, we're going to do equations next. This question next asks us to determine the values where these graphs are equal. All right. So I know this is a bit of a jump because we haven't reminded ourselves how to solve these equations. But let's see if we can find what look like these to be these 3 points where these graphs cut one another. Okay. So let's take a look. When we have cos, we're going to put them equal to one another. In other words, we're going to solve them simultaneously. We've got cos 2 theta equals sine theta. When we've got cos and sine in the same equation, but not acting on the same angle, then there's a trick that we need to perform. So our challenge here is that we actually needed the graphs to look at the equations, but we also need the equations to look at the graphs. So I'm going to just quickly solve this equation for you, and hopefully it'll make a little bit more sense next time if you watch it after you've watched the equations video. Right, what we've got here is we've got cos and sine in the same equation, but not acting on the same angle. If they were acting on the same angle, we could divide both sides by cos, and we could change to tan, and we'd have a kind of a vanilla flavored trig equation. What I'm going to do here is I'm going to use my co-ratio, and I'm going to go sine of 90 minus 2 theta is the same as sine theta. And now I've got a situation where I've got kind of sine of A equal to sine of B, right? And the most obvious solution to that is, in fact, that those two angles are equal. In other words, that 90 minus 2 theta equals theta plus 360k, right? But another alternative is, remember that A could actually equal 180 minus B, because sine of 180 minus B would also be the same as sine of B. So another possibility is, and I'm just going to leave a line for some working here, is that 90 minus 2 theta equals 180 minus theta plus 360k. What I'm going to do is I'm going to solve both of these. I'm just going to change pen color, it might make it a bit clearer. So if I subtract theta from both sides here, I'm going to get minus 3 theta. And if I subtract the 90, I'm going to get minus 90. So I end up, if I divide through by the negative 3, I end up getting theta is 30 plus 120k. Right? And from here, I'm going to get minus theta. If I add a theta to both sides, is 180 plus 360k. Somewhere on this page I need to just confirm that in fact k is an integer. Right? And now if obviously this one's the same as saying that theta is negative 180 plus 360k. Okay, so if we start trying to look at where are these graphs equal to one another, right? We had the 30 plus 120k. Well, that's clearly 30 when we don't add any, in other words, when k is 0. This one here is going to be 30 plus 120, it's going to be 150, right? And if we add another 150, we get 270. Sorry, another 120 rather, we get to 270, so that's that point over there. Okay, the question then, yeah, it doesn't look like we got any solutions from here, and in fact something, I think I've messed up something here. This should be 90, and so in fact theta is minus 90 plus 360k, and the only one we get out of here is in fact the 270, which we've already got. The question then asked, where is cos 2 theta minus sine theta less than or equal to 0? Now, if I add sine theta to both sides of that, I'm actually saying where is cos 2 theta less than or equal to sine theta? Remember, the cos graph is the red graph, the sine graph is the green graph. We're asking where is the red graph below the green graph on this domain? Right, and it's below from 0 up to 30, including 30, right? Or from 150 the whole way through, in fact, to 360. It's below or equal to the green graph. Okay, so that's a sort of an interpretation question on graphs.